So, hello, and before we start the presentation about why should I choose SLS benchtop technology, I think an introduction is required. So my name is Konrad Kobus. I'm a mechanical engineer working in the research and development department at Sinterit. I have over 7 years of experience in machine design, robotics and mechatronics. Back when I was working at the Department of Robotics and Mechatronics at the AGH University of Science and Technology in Krakow, I had the opportunity to work with several FDM printers, learning their pros and cons to the largest extent possible. And now I'm working on the SLS systems, having a lot of fun with them, because I truly think that this is the technology of the future. So, today I would like to talk about the SLS technique of 3D printing and its advantages in comparison to other printing techniques, in this case the FDM and SLA ones. So the agenda for today's webinar is as follows. I will start by posing a few questions and later on answering them. So first of all, what exactly is SLS in general? Which methods of 3D printing require support structures and why it's necessary to be able to print without them, and why they are not needed while printing objects with the SLS method. Why is SLS technique the most cost and time efficient of all additive manufacturing processes, at least in my opinion? Why is SLS one of the best ways of printing detailed objects, and why those printouts possess higher durability and stiffness, and why they are fully movable at the same time? And also I would like to say a few words about the properties of materials used for printing in SLS. So after the presentation, Ada, our international sales manager, will join me, and together we will answer your questions. So please feel free to write them down during the webinar, and without any further delays, let's get started. So, we must start with the basics. What exactly is SLS? The abbreviation or acronym stands for Selective Laser Sintering. It's a process during which powdered material is heated up and smelted by means of additional energy provided by a laser. A layer of powder is rolled across the top, and then it's fused together. The process is repeated until all layers are sintered into one durable object. Aside from powder removal, no post-processes are needed. Of course, you can always polish, paint, or apply a dye or a varnish, but that's really up to you, and it's not something that's really required in order to have a fine printout. What are the differences between SLS, FDM, and SLA printing methods? Well, there are all different techniques, different approaches to 3D printing. FDM stands for Fused Deposition Modeling. It's a process during which the model is produced by extruding small flattened strands of molten material, forming layers as the material hardens immediately after extrusion due to lower temperatures outside of the extruding unit. And the SLA acronym describes stereolithography. It employs photopolymerization using light to link chains of molecules together and form a polymer 3D structure. All of those methods can be seen as forms of microscale clay modeling or clay making processes, but they are using different methods to glue the structure together, and so they are all additive manufacturing processes. But let's get back to the SLS. For example, our printer, the Sinterit Lisa, offers the ability to print in high resolution without losing even the smallest details. The walls printed with Lisa can be as thin as 0.4 millimeters, so in imperial standards that would be 0.016 inches, and that allows you to create really precise models. What's more, Lisa can print complicated figures without any support structures, and that's basically a game changer. The usage of laser technology opens up completely new possibilities when it comes to 3D printing. I am talking here about things that were and still are practically impossible to do with the FDM or SLA techniques. For example, you can print fully movable objects and you can do it all in just one print. It's also possible to make your designs flexible and detailed at the same time. But let's get back to SLS. For example, our printer, the Sinterit Lisa, offers the ability to print in high resolution without losing even the smallest details. The walls printed with Lisa can be as thin as 0.4 millimeters, and in imperial standards that would be 0.016 inches. That allows you to create really precise models. What's more, Lisa can print complicated figures without any support structures, and that basically is a game changer. Usage of laser technology opens up completely new possibilities when it comes to 3D printing. I'm talking here about things that were and still are practically impossible to do with FDM or SLA techniques. For example, you can print fully movable objects and you can do it all in just one print. It's also possible to make your designs flexible and detailed at the same time. So let's talk about the advantages of SLS, one by one and in more detail, and by extension about our Sinterit Lisa printer. The main advantage of SLS technique over FDM and SLA is the fact that there is no need for structural supports. Prints made in an SLS printer are self-supported. In other words, material used for prints like nylon-based powders or compounds of plastics and silicone mixed together acts like support for the entire structure itself. At first glance, the requirement of having structures supporting your prints can seem like something that only takes time. And of course, it's not like time isn't money, so the ability to forego that requirement is already valuable on itself, but it goes even further than that. You see, having support structures can have an impact on what you can or cannot print. SLS technology allows you to print even the most complicated models in just one piece. The efficiency when it comes to both costs and time should be obvious, not to mention the freedom of form it gives you, especially when it comes to building complicated prototypes. Some of them can be quite expensive when making them with conventional methods like machining or molding or casting. Some of them will be impossible to make otherwise than using an additive manufacturing processes. You can print complex figures with interior elements as well as channels, grooves, canals, and so on. Just look on this model. It's basically impossible to print this with a standard low-cost FDM desktop printer. And now let's see what we have here. Can you see all those supportive structures? Removing them will require a lot of time and effort. With SLS, you have your prints instantly ready to use. I will admit though that the SLS models presented on this and other slides are already sanded, while the FDM ones are taken straight from the printers. But even so, it will require a lot of mechanical and later on chemical post-processing to have your FDM prints come close to those out of an SLS printer. Here we can see a comparison between a printout being a universal joint or a cardan joint from Lisa on the left side and from a basic desktop type FDM printer on the right side. And on this photo you can see a print of a bicycle derailleur from Lisa with comparison to a printout from a highly sophisticated industrial FDM printer. With the first comparison, you can clearly see the difference. You can argue that you could use a dissolvable filament to print it, but from my experience, printing supports from that kind of filament almost guarantees a failed printout due to the fact that not many materials stick properly to them. And even if you will still have undesirable artifacts in places where the support structures were present. Then there is also the warping problem and so on. And as for the derailleur, you can also see different artifacts on the FDM printout, but let's say that they are all the same. They are all the same quality, okay? Now let's look on the prices of the printers. So Lisa costs 6,000 euros. A reasonable desktop FDM costs on average about 2,500 euros. I know that you can buy cheaper ones, but their reliability is questionable at best. And the industrial FDM printer on which we printed our model costs about 25,000 euros. But let's go even further than that. What is the cost of the actual printout? The derailleur printed by Lisa costs about 100 euros, and that's the price that we are charging for it if you would like a sample. And from the industrial FDM, it's about 250 euros. So add to it costs of post-processing, so additional machines, time and qualified staff. And now I think the answer is much more clearer which printing technique is more time and cost efficient. No need for structural supports give you another advantage. While using an SLS technique, you can print multiple objects at once. The process is called nesting, and let me show you how it works using this simple example. So as you can see here on this picture, you can print not only one layer of elements, but on top of that layer, you can print another one, and so on, so on. So if you will have elements positioned like this, they will still be printed. Also, if you have some sort of gaps between the layers of elements, you can also place or position a smaller elements to fill in that gap, and therefore you will have the full possibility of printing with the entire workplace of the machine, okay? So not only can you print multiple copies of the same object, but also several models at once. The printing will take longer, that's true, but it's still faster than printing all the pieces one by one. You may ask why. The answer is because of the additional time you need to prepare a 3D printer for another go. So this is something that's completely impossible to do with an FDM or SLA printer because of the need for support structures. Being able to print multiple objects in one process makes SLS method the fastest currently known on the market. FDM only allows you to print one layer of prints at the time. What's even worse, because you can't print more complicated forms in one piece, with an FDM printer you basically have to print elements one by one. The more complicated model you print with the FDM printer, the more time you need to receive the final product. SLS technique, in comparison, gives you the ability to print the same complicated model in one go, with all parts already there. Wall thickness is one of the most important parameters that describe how detailed the prints can be. Minimal wall thickness that you can acquire while printing with the SLS Lisa printer is 0.4 millimeters, so 0.016 inches. You can't get them any thinner than that right now, but it is possible. The minimal thickness depends on the diameter of the laser used in our system. So if you would like to have even thinner details on your prints, say 0.1 millimeter, we would need to install a laser with a spot diameter of 0.1 millimeter. But you have to bear in mind that the smaller the laser spot you have, the longer the printing time will be, because of the time it will take for the laser to print just one layer, and it will be 4 times longer. So I would say that the 0.4 millimeter laser spot diameter is something of a compromise between the printing time and the level of details you can achieve. But still there's more advantages, like the layer thickness. For example, Sinterit Lisa can make a layer as thin as 0.075 millimeters. So in imperial standard, that's about 0.003 inches. And this gives you the option to print really precise objects. This element, for example, being a tensile stress test specimen, was printed with an FDM printer. You can see the layers are clearly visible. Of course, there are some processes that can help you to smooth it, but this is how the object will look when you will take it straight from the printer. And again, time is money, right? And here you can see the same object, but printed with the SLS technique. As you can see, there are no visible layers and the object is quite smooth. To examine how durable the printouts are, we use several well-known measures. One of them is the Sharpie impact test, which determines the amount of energy that is absorbed by a test specimen during fracture. For our examination of the PA12 smooth material, we use a pendulum with maximum energy of 50 joules. The maximum breaking energy of the Sharpie U notch test sample is 5.23 kilojoules per square meter. With the V notch, the energy needed is lower and reaches 3.28 kilojoules per square meter. The second measurement is the tensile stress test carried out on the universal testing machine. The specimen is being stretched, and compared with its elongation, the useful engineering data can be obtained. So, for example, the Young's module that is 1.8 gigapascals or 0.26 megapound force per square inch, or something called ultimate tensile strength, which is 41 megapascals, or in imperial standards that would be 6 kilopound force per square inch. The high print accuracy with the SLS technique that I mentioned a moment ago gives you the possibility to print fully movable objects or movable parts. So, we reached the last but surely not the least important topic concerning SLS technique, the materials and their properties. It's really important to see how adequate the materials used in printing will be for your needs. Materials used in SLS printing are based on polyamide powders. In case of Sinterit Lisa, we are using PA12 compound. We are also using the TPU or thermoplastic polyurethane Flexa Black material, but we will talk about all of our materials in more details in the future. Right now you need to know that Flexa Black, as its name suggests, is really flexible and gives you the possibility to print really elastic objects. The most important thing about PA12 is its melting temperature, and it's about 180 to 183 degrees Celsius. It's also highly resistant to chemical substances like acetone, petrol, glycerin, methanol, etc., etc. It's also worth noting that PA12 is also resistant to ultraviolet radiation as well. So lately we have also introduced new Flexa Gray material with better flexibility and PA11 with higher tensile stress, superior impact durability, and better chemical and temperature resistances. In comparison, materials commonly used to print with any FDM printer have worse chemical resistances, and the same goes for materials used in SLA printing. FDM materials are temperature resistant, however SLA materials aren't. So these are the most important advantages that the SLS printers have over other 3D printers using FDM or SLA methods. It's truly an amazing method of printing, and you can have a printer that can produce such a high quality objects for such a low price, compared not only to other SLS printers but also other industrial FDM or SLA printers in general. Lately we have also introduced another printer called Lisa 2 Pro for professional, and more information about both of those printers you can find on our website www.sinterit.com. To stay updated, make sure you are following us on Facebook, Twitter, YouTube, or all of these channels, why not? And I hope that you enjoyed this part of the webinar and found it quite useful or maybe informative. Now we can answer your questions. Ada is already here with me, so without further delay, let's start answering your questions. I think we'll start.
Okay, I hope you can hear me. So we are waiting for your questions. You can write them on the chat and we will show them on the screen. So if you have questions, please write them on the chat.
I hope you'll have some questions, because I know that the webinar was very general. Sometimes there were some very specific informations, but I hope you will have some sort of questions for us. This webinar is basically for you. Okay, so the first question is, how can I get a gloss flat finish on the printed parts?
So first of all, from the printer we're receiving the part as you were shown on the pictures, but everything can be obtained by post-processing. You can use specific machines because they're developed now especially for SLS printing. And you can use some base and also spray painting or other post-processing to receive such glossy parts.
Yeah. So to add something to this, because we had questions about the roughness of printouts. After sanding, just sanding, the parts have roughness of about 6.34, I think, RA. So that's the parameter of the roughness. So it's maybe not that gloss and it's not that smooth, but as Ada said, everything can be obtained by applying a base.
Some post-processing with painting.
Yes. So how many times does the laser charge can be used? How many times? Wow. We have some sorts of statistics that says that the laser, the lifetime of a laser should be 10,000 hours of work, but really how much time it would be when you are printing, let's say 24 hours a day and so on, a couple of years. And even we have a customer that has our printer, I think for 2 or 3 years by now, and the printer is still printing, the laser is fine and well. And, you know, this is something that is just a statistic, okay? So statistically, 10,000 hours, okay, statistically. But as you heard, it can be more and more, yes? So.
Yes, so if you have more questions, we are waiting. Someone is writing, I see. So
okay, that's good.
We are waiting.
Try to get from this webinar as much as you can. So how is stand regarding delivery time of Lisa 2? Wow, that's a tough question here, and I will answer this question.
Okay, we have now a reservation system, so we have a lot of reservation now because from June we released this option for you, and now the very time if you you are filling the form, reservation form, it could be January, February rather, because of the lot of reservation. So you can visit our site and fill in the form and we will send you exact information. However, due to the long list, it could be a little longer for you now. So as you can hear, they are selling like cupcakes or hotcakes or whatever. Yeah, it's yeah, we have a lot of yes, we have a lot of reservations. So yes, please fill in as soon as possible because every day we're receiving some. It's a hot product. Yes. So next question is, your Lisa Pro uses nitrogen, if I remember correctly. Is it to avoid oxidation or? So yes, but not only nitrogen. We have gas inlet in Lisa Pro, and you can in fact put other gas also. However, nitrogen is good for PA11, for example. It is necessary for printing from this material. So basically, you would get a machine. The Lisa Pro is a machine that is fine for experimentation, because as Ada said, nitrogen is something that we were testing, and we had
excellent results with the PA11 and also the Flexa Gray and so on and so on. But yeah, you can put all sorts of gases in there, like argon or other gas, and you can experiment with the powders you have. Maybe you are a person that has a company that produces powders for the SLS industry. So this is an experimental, not an experimental machine because we've already tested the machines and everything is fine and well. But it's an experimental machine for the customers. Yeah.
And other question, can I see Lisa to on the show in Frankfurt? Of course, so you are invited to see the our new device. So we will show this device on the fairs. And we soon, I think, make some appointment reservation list on our page. So be in touch and look at our page. Some information will be announced soon, I think.
Yeah, and I think this is not a product that we would like to place in the locker or whatever. We would like to show the printer on every affairs and so on, so on. So yeah, I think there's a guarantee that you will see the Lisa Pro. So can you tell us a little bit regarding reuse of powder or mix percentage? Yes, we can.
Okay, so this is mainly for PA12 problem issue about, maybe not issue, but possibility. Regarding Flexa Black and Gray, you have 100% reusable, so you don't need to refresh it.
Yes, that's very important because sometimes our customers are confused with, I think, 100% reusability or something like that. Yes, it means that the used powder from the prints printed from that material, you just have it. You just put it in another machine or the same machine, and you print more next and so on.
Of course, we talk about this loose powder which you take out from the printer after the process. And regarding the PA12, this powder we take out from the printer, we count as 70%, and we have to add 30% of fresh PA12 to get this again printable. So this is our print ready PA12 powder.
Yeah.
In fact.
So basically, if we have, let's say, 1 liter or 1 kilogram of the powder used for the print, you would have to add 30% of it, so 300 grams or 0.3 liter, and so on and so on. Okay.
Yes, that's right. So I think that's all. Someone write something.
Okay, so one last question,
yes.
Okay?
Oh yes, I think one last question.
We would like to answer more, but
you can write to us by mail also. We will write to you as soon as possible.
Yeah, and you also have the possibility to ask questions on the fairs and also on the next webinar. Can you tell me the clear opening dimensions, of the sieve? Maybe of the sieve. Are you talking about the sieve that we have, the little black sieve which you are sieving the powders, or?
If you could write more details, what?
Yes.
Yes, sieve.
A sieve. Yes. So the question is, yes. So how much powder we can no, the diameter. Okay, the diameter. I think the diameter is about 30 centimeters in diameter, I think. And I think it's about 10 liters of powder. 10 of, yes, I think 10 liter of powder, yes. So basically, okay, so the diameter is 30 something centimeters because we don't have it right now in our room, so we can't measure it, unfortunately. But you have 5 to 10 liters of powder that can be.
Dimension of the mesh.
Oh, dimension of the mesh. Oh, okay. So the dimension of the mesh is, I think, 160 micrometers. So 0.16 millimeter. Okay. Yeah, and it can apply to both PA12 and also the TPU, the thermoplastic polyurethane materials as well. But we are, of course, we are working on the possibilities to have even smaller mesh window, but I won't talk about it anymore. So.
Okay, so I will respond to your last question about the samples. Yes, of course, you can write to us of contact@sinterit.com, and we can make samples for you from your own STL designs also. And we can send you whole prices, the offer, what do you need. Just write to us and we will respond everything you need. So I think we're finishing.
Yes. I think this is really everything we wanted to say. And once again, I hope that you've enjoyed the webinar. Please fill in the short questionnaire if you would. It will help us to do what would you like to know about the SLS phenomena, what would be the topic of the next webinar, and so on. We want to hear your voice about it. So thanks for watching, and hopefully till next time, yeah, see you there.
Yes, see you on the fairs in Frankfurt.